All right, so this is question 6 of the practice test. We have a rigid tank, contains 1 pound mole of argon at 700 degrees Rankine, 750 psi, and then we open a valve and we add some nitrogen. So we've got 3 pounds of nitrogen that comes in at 500 degrees Rankine and 1200 psi. So this is just a little bit different from what we've done in 2 other kind of closed system mixing problems. This is just a little bit different because we start off, kind of look over here, we start off with a tank and all we've got in it is argon. And then we open a valve and we put some nitrogen in and we allow it to come to equilibrium until the final temperature is 620 degrees Rankine. So it's a little bit different. So we just kind of have to keep that in mind. And we want to find some stuff. So I know the solution is online, but it might be helpful to have somebody walk through how we got the numbers that we got. So let's go ahead and fill in our little table here. Don't worry about the CV and CP so much, or the R. Really, it's just, you know, what we're used to is this, well, not that far, but just this part right here, okay? So let's see what they gave us. They gave us the pound moles of argon and nitrogen. So those are 2 things that I could put in there, right? So I can put the number of moles for each of those components, and then that allows me to calculate the total number of moles. Great, I got 4. So now I can calculate the mole fraction. So that should be good. Perfect. I can also go ahead and at least start filling a few things in. I can look at table A1E and get the molar mass for argon and nitrogen and throw that in there. And then I could say, okay, well, in 4 pound moles of this mixture, I would have, based on that molar mass, you would have, if you had 1 pound mole of argon, well, the mass you would have would be 1 times 39.94, or 39.94 pound mass. Same thing with the nitrogen, it'd be 3 times 28.01. Okay, so we've mostly filled things in, and I guess, yeah, we can add those 2 masses up, get the total mass, and from there we can get the mass fraction. So I've got really kind of everything that I would normally want to get in that table. And so now I need to get the other stuff. So I need to get the molar mass of my mixture. And so what you could do is you can use, I know it just says, you know, the molar mass is the sum of the mole fractions times the molar mass for each of those components, but the numbers that you're plugging in that 0.25 and 0.75, right? This guy and this guy, and then their respective molar masses, right? And that should give you 30.9925, and I just kind of put a little placeholder on that little readout up at the top. Perfect. All right. Just by the way, I do have a little thing right here. This is not necessary. Well, I guess it was, because I think the next thing we're calculating, we're calculating the specific gas constant of our argon. So your specific gas constant is just for any gas, it's R bar over your molar mass. So for this, we're doing the R bar over the molar mass of our argon, which is 39.94. So 1.986 divided by 39.94, and that would give you BTU per pound mass degree Rankine. And you could do the exact same thing if you needed. You could get the same thing for your nitrogen as well. So that's the other number there. It didn't ask for it, I don't think, but we have the information there. If you did want to get this guy, your specific gas constant, you could. So your R, this is going to be R bar over your molar mass of your mixture, and we have that molar mass of our mixture. This is the 30.9925. Yeah, so this would be 1.986 over, what was it again? 30.9925. 30.9925. Right. This is BTU per pound mole degree Rankine, and this is not BTU, but pound mass per pound mole. Yeah, and so that should give you a specific gas constant point 0.6408, and so that's the other number that was missing there. Okay, again, I don't think it was something that was asked for, but yeah, if we need it. All right, so this one I think is the one that might have thrown people off. So we wanted to find the pressure of the mixture at state 2. So for this guy, well, I'm going to use my ideal gas law. So I could put this as MRT over V, or I could put it in terms of moles. I have the number of moles. Remember, I had 1 pound mole of argon, 3 pound mole of nitrogen. So I've got 4 pound mole of my mixture at state 2. R bar is my universal gas constant. T2 was given to me as 620 degrees Rankine, and then V2 is question mark. I don't know that. However, I kind of remember what was going on here. So remember, we started off with just argon in the tank, and then we added nitrogen and allowed everything to come to equilibrium. So if we kind of see it in a picture, it might be a little bit more obvious that the volume of that argon initially is the volume of the mixture at state 2. So if I use the parameters at state 1 for the argon, I should be able to figure out the volume at state 2. So I'm going to do that. So I'm going to apply my ideal gas law to that argon at state 1. So I've got the mass times the specific gas constant. Oops, and that should be of argon. That would be an important thing to note, right? Or let's put this in terms of moles. Let's fix that. Number of moles of argon times R bar times the temperature of the argon over the pressure. Notice that because I've got things in terms of N and R bar, you do need to divide by your, actually no, wait a minute. To have something a little bit squirrely. Oh no, this is fine. This is fine. Sorry, that's fine. Yeah, because if I keep this as mass, this R bar divided by molar mass, that is the specific gas constant of my argon. So, okay, perfect. All right, so I had calculated, remember if you look up at your table, we do know the pound mass or the mass of the argon. R bar is the 1545. The temperature is given to us as 700 degrees Rankine. I know the pressure is given to me 750. Again, the molar mass is not pound. Oh, I think I got excited there. The molar mass is not pound force per inch squared, but it is pound mass per pound mole. Perfect. And then I just need to reconcile my units and get things in terms of feet cubed. And there we go. And then, of course, I know that initial volume of the argon is going to be the volume at state 2. And now I'm just going to plug things in to get that volume. So apply my ideal gas law in R bar T2 over the volume at 2 divided by the volume at 2, which I just calculated to be 10.01389 feet cubed. Yeah, do again have some unit conversions. Maybe I should have just left it as feet cubed or inches squared before, but yeah, what are you going to do? But I've got 2657.901 pound force per inch squared. So again, the key part that might have like messed people up is that little bit right there, that the initial volume of that argon is really equal to the final volume as well. All right, so next part was figuring out what the specific heat of our argon was. And if you look in table A20, you notice that argon is not there, and so it's kind of hidden. So I've got it pulled up right here. So this is table A21, and there's this tiny little bit of text down here. So it says for monoatomic gases such as helium, neon, and argon, which is what we have, Cp bar, right? So Cp in terms of BTU per pound mole degree Rankine is very nearly equal to 5/2 times R bar. So if your R bar was 1.986, then you would have 2.5 times 1.986 BTU per pound mole degree Rankine. That would be your CP bar. And so with that information, let's go ahead and get rid of that. So that little piece of information, 2.5 times R bar, or 5/2 times R bar, that was in table A21. And so the next thing I did is I just, okay, 2.5 times 1.986, that would give me 4.965 BTU per pound mole degree Rankine. Of course, they wanted our CV value. And so the piece of information that you need there, well, number one, you need to get this thing in terms of pound mass as opposed to pound moles. So your magic number to go between mass and moles is your molar mass. So if you divide BTU per pound mole degree Rankine divided by pound mass per pound mole, you're going to get BTU per pound mass degree Rankine. So yeah. And then that takes care of your CP, but you need your CV. And actually, let's go look. Oops, not that. Yeah. This is actually, it's an ideal gas relationship, but nope, that guy right there. So your CP and your CV are related by your specific gas constant. And so I know that CP is equal to CV plus R. And if you recall, we actually did calculate our R for each of these guys. So this R for argon would be 0.0497. So 0.0497, right? If your CP, if this guy is 0.1243 BTU per pound mass degree Rankine, and your R bar was, what did we say, 0.0497, 0.0497 BTU per pound mass, then your CV for that argon should be 0.0746 BTU per pound mole. BTU per pound mass degree Rankine. All right, and then the very last thing that we're supposed to do is figure out the specific heat for our nitrogen, which isn't nearly as bad as the other one. This is just because I know the initial and the final temperature, right? Your initial temperature was, what was it? Actually, I think I've got it up here somewhere. Yeah. So for your nitrogen, if your initial temperature was 500 and your final temperature is 620 degrees Rankine, that would make your average temperature 560 degrees Rankine, or just about 100 degrees Fahrenheit, which is very convenient. And we can look at table, this would be in table A20. A20E, and you can look up that CV at 100 degrees Fahrenheit and get your CV for that. All right, so hopefully that was helpful. Thank you for watching.